by wide spaces. As I cradled Miss Gray's brain in my hands, I remember marveling in much the same way I had on the day Sarah was born. In my hands were 3 pounds of cells that had powered an entire life. It was the very essence of that life, the neurons, the connections that spurred Mrs. Gray to volunteer at the library on weekends, smile when she saw her grandson's face, or get grumpy when she was stuck in traffic. Huh, Mom? What do you think about that? In between the moment she had seen those bright delivery room lights and the moment her last neuron had fired, every experience her brain had encountered shaped the person she became, and yet no one at the time would have suggested that how she lived her life as an adult had substantially altered the size and structure of the brain. At the time, it was mid-1990s, the human brain was widely believed to finish its development and become fixed in structure by childhood. After that, there would be only one inevitable possibility for structural change. The brain would shrink with age. That's what everyone thought. But, as you'll soon learn, everyone was undeniably wrong. Your brain, baby. What happened to Mrs. Gray's brain in those 85 years between birth and death? And how did changes inside her brain affect the cognitive abilities throughout life? How might she have steered those changes in one direction or another? And to what end? Mrs. Gray's story started the same way that Sarah's had, with a tiny clump of cells. I'll stick with the simple version of brain development and aging, but even simplified, it's an incredible tale. Human life, after all, begins as one cell and ends with some 100 billion in the brain alone. 100 billion in the brain alone. We can start the story of Sarah's brain by taking a peek inside her mom's uterus at about the 3rd week of gestation. Remember those dividing cells? At about this time, some will form a column of cells the shape of a tiny tube. At one end of the tube, cells will develop into a spinal cord, while at the other end cells will develop and form a brain's 2 hemispheres. Most of these cells become neurons, and at one end will have extensive branches, tens of thousands of them, called dendrites, which will act as antennae to receive input from other neurons. At its outer end, each neuron will sprout a single long extension called an axon, which in turn will sprout at its tips tens of thousands of swellings called axon terminals. Within Sarah's brain, these neurons will begin to send messages to each other via electrical signals that leap from the axon terminal of one neuron to a special docking site on the dendrite of another neuron, crossing a gap called a synaptic cleft. Eventually, the brain will contain more than 100 trillion such synaptic connections. As Sarah grows, 100 trillion connections. As Sarah shows in her mother's uterus, as Sarah grows in her mother's uterus, her brain will continue to form as a sheet of cells called the cortex, which develops rapidly and extensively, so much so that the folds on itself hundreds of times, giving the outer portions of the brain its cauliflower-like appearance. Other brain structures will develop beneath the cortex. But it is the cortex that all of Sarah's higher cognition will take place. This is ground zero for her future memory, attention, perceptual awareness, thought, language, and ability to make decisions. Sarah's cortex in either hemisphere will further develop into 5 symmetrical lobes, which are recognized by landmarks on the surface of the brain and form in roughly the same place from one person to the next. Each lobe, roughly the size of an orange, will contain several billion neurons, which will exchange trillions of messages with each other, with neurons in the other hemispheres, and with deeper brain structures. The cortex in the frontal lobes, just above and behind Sarah's eyes, will develop to handle planning, execution, and control of movements. In the right hemisphere, her frontal lobe will be particularly tied to art and music, appreciation as well as intonation and speech. In the left, it will be tied to logical thinking, concentration, and understanding symbols in reading and writing. Near the ears, Sarah's temporal lobes will develop to handle her sense of hearing and understanding language, among other things. Deep within each temporal lobe, the hippocampus will form. It will be key to all aspects of memory. Between her frontal and temporal lobes, the parietal lobes will develop to handle various sensory inputs from the skin. They will take charge of Sarah's sense of touch, her ability to feel weight and motion, proprioception, and sense of knowing where parts of the body are at a given time without having to look, and self-orientation. The parietal lobe in the right will help her with navigation, while the parietal lobe on the left will deal with calculation. At the back of the brain, the occipital lobes will form. Occipital lobes will form. They will handle vision and will be integral to the recognizing of familiar face and detecting constellation of stars at night. Sarah's optical lobe, occipital lobes will enable her to both see and make sense of what she sees. Sarah's forming brain will also include a limbic lobe, a connection of cortical areas in the frontal and temporal lobes, plus some deeper brain structures. One is the amygdala, an almond-shaped structure. Actually, there are 2, one in each hemisphere, which is tied to emotions. Another component of the limbic lobe is the hypothalamus, which regulates hormones involved in the person's flight or flight response, eating and metabolism, and is closely connected to the amygdala. That's right. Both the amygdala and the hippocampus are closely linked to the hippocampus. Hypothalamus and amygdala are closely linked to the hippocampus. The various parts of Sarah's cortex will communicate with each other and with a dozen deep brain structures as well as the spinal cord via nerve bundles which act as highways between the brain. As Sarah's brain develops, it is the conversation between neurons. Those electrical signals pass and receive that keep them alive and connected. When they fire a signal across the synaptic gap, they strengthen each other, riding them together and increasing their chances of survival. Wiring them together and increasing their chances of survival. Neurons that fire together wire together, as neuroscientists like to say. Neurons that don't fire and wire see their connections cold and shrivel away, which happens later in life through the phenomenon called disuse atrophy, or the use it or lose it principle. This process is critical during the initial stages of brain development, but persists throughout life, a fact that is critical in our quest to grow the brain, as you'll soon read. In the weeks before she was born, Sarah's brain will continue to rapidly develop so that by the time she enters the world, it will be about 90% complete. Important areas needed for survival will have developed fully in order to ensure that she breathes, sleeps, and sucks when presented with anything that resembles a nipple.